we will be doing derivatives all year long. There are two things we do on the AP test. If you're stuck and you don't know what to do, choose one of two things. One is take the derivative. The other is the antiderivative. Go the other direction. Kind of like squaring, square rooting. It's pretty much everything we do in calculus will boil down to one of those two things. Very general, but ish. So we picked up last year some of the details about how to find a derivative using the shortcuts. The derivative is this stuff that you were doing today, limit of the difference quotient, big, long, involved. And as the equations become more difficult, that would become more difficult. So conveniently, there are some shortcuts. There's ways to get there. Understand, there's a ton of mathematics behind these shortcuts. We don't need to worry about it. Other folks have figured it out for us. We just get to use their answers. So that's a good thing. Start with some of these ones. This is, I think, the notes that I actually gave you guys last year on some of these. But let's start kind of at the beginning and work our way back up. Horizontal line, y equals 3. Now remember, the derivative is the slope. So what's the slope of this line? 0. Undefined, 0. Slope is 0. And so the derivative of that function, y equals 3, is f prime is equal to 0. That's true for any constant. The derivative of a constant is 0. Notation-wise, this d over dx of a constant. D over dx is, think of this as dy dx. In physics, you probably use delta y and delta x, yes, for that notation. Dy dx. So this is the function in this case. You could think of that as dy dx, but in this case, it's just a constant. Leibniz is the brief history. Newton, Sir Isaac, and Leibniz kind of developed calculus independently of each other. If I'm not mistaken, if I remember the story right, Leibniz developed it later than Newton. Newton kind of came up with it first, but was unsure of his findings and didn't publish. Leibniz published later, developed it later than he did, but published first. And then once Newton saw his stuff, then he published his information, and then there was like big battle about plagiarism issues, and you stole my ideas, and anyway, I don't know if they got it all worked out or if they had to duel at dawn. But each of them has some notation that in today's calculus we kind of use. Sometimes it's better to use Leibniz, sometimes it's better to use Newton. The Newton is more of the f of x stuff. Leibniz does this d dx. All right, talk about a different kind of equation. Y equals 2x minus 3. The derivative is the slope. What's that slope? 2. And where is the slope 2? Everywhere. And so the slope of this line is 2 everywhere. Notice that there's no variable in that answer. There's no varying the slope. The slope of this line is 2, and it's 2 everywhere. The derivative of a constant is, the derivative of a linear equation is just the m. Y equals mx plus b. It's the slope of the line. So that derivative is that. Now where I'm going with this is kind of developing the pattern to begin to see the derivative a little bit. And again, that's what I was saying. The derivative of a line is always a constant because the line constantly has the same slope, 2. That's kind of one of those little intuitive kind of, oh yeah, straight line, it's always good. Now a curve, where the slope changes, depending upon where you are, the derivative is going to have a variable in it. If I had the line y equals x, or the function is x, the derivative of that is just 1. So the derivative of x is 1. The slope is 1. All right, so long involved process we could do using the limit of the difference quotient. But if we remember from last year, these are the derivatives. And the pattern, of course, is with that. You say it looks like a pattern. Yes, it does. Good for you to recognize it's a pattern. Thank you. I was feeling excited that day. This is the pattern. Remember, the exponent multiplies down into the front, and then the exponent gets smaller by 1. So the exponent n multiplies down to the front, exponent gets smaller by 1. That's the shortcut for polynomials. Called a power rule, because it's something to the third power. If there's constant out front, you can just ignore that constant, bring it out front, take the derivative of the functions, and then multiply by the constant again. Now, we almost never use this notation. No, let me rephrase that. You won't really ever have to write this kind of a notation like this out, but you should be able to read, recognize, understand what that notation says, and not be freaked out by that notation. You should see this as the derivative of, some function, and then, okay, all I've done is pulled that constant out front, and then I'm taking the derivative of the function. Be comfortable with the notation, be able to read it. Read this as the derivative of c times f of x. So what that meant was, if I have some constant out front, then we're going to ignore that constant for a minute when we take the derivative, and just take the derivative of the function itself. So I can pull the 2 out front, get the derivative of this guy, and then multiply by the 2. Now the shortcut is, of course, you just multiply it, right? So the shortcut we're going to do is 3 times the 2, 6, and then the exponent gets smaller by 1. Every once in a while, you're going to see a problem where they have a constant out front, and it's going to look way complicated, and you're going to go, oh yeah, you just take the derivative and you multiply by that constant at the end. Again, very complicated looking thing, but look what this says. I'm taking the derivative of a sum. Well, the derivative of the sum is the sum of the derivatives. Now, don't write this out. Just look at it. And because we've already done that. We already did that. This is a function. And if I wanted to take the derivative of the sum, I just take the sum of the derivative. So I take the derivative of the first one, I take the derivative of the second one, and just add them together. So, but again, be able to look at that. It looks really impressive, right? It looks like big math going on. And it is. I mean, it's calculus. But it's really simple. But I want you to be able to read that and understand that and look at that and go, yeah, okay, I see what's going on. The derivative of the sum of things, derivative of the first one, derivative of the second one. No problem. And that's what's going on in there. All right. Same thing, except instead of being a sum, it's a subtraction. So it doesn't matter whether you're adding or subtracting. So in other words, a polynomial, derivative of the polynomial, just take each of the terms one at a time, take their derivative. Got it. Here's where things get a little trickier, and I don't think we talked about this last year, so jot this one down. This is a multiplication. Right. Wow, that's connected to that one down there. Leibniz notation and also with Newton notation. The two different kinds. Almost never do I write the first one. Almost always I'll write it in the second form. But here's how I say this. derivative of the first times the second plus the first times the derivative of the second. Now the book may have it in a different order because however I add these two things up right here, because it's addition, it doesn't matter if I do this one first and then this one or vice versa because it's addition. I think the book might have it in the other order. I learned it this way, and so that's the way I'm stuck with. I'm an old dog, can't teach me a new trick. Doesn't matter. So what I'm doing is I've got two functions being multiplied together. You take the derivative of the first one times the second one plus the first one times the derivative of the second one.
So for the ones in brackets, you're not taking the derivative of it? You're just
Correct. That's just times the original function. So something like this. This is a product, right? X squared times derivative of x. Now I could do this a couple of ways. But let's pretend it's two functions for a minute. I'm going to call the first one g of x, call the second one h of x. So according to the rule, what I need to do is the derivative of the first one, that's that, times the second one, that's that, plus the first one times the derivative of the second one. That's the pattern to this. And again, lots of math went into figuring it out. We just get to use the answer. So derivative of x squared is 2x times the second. Doesn't change. Plus the first times the derivative of the second. Now, what I did is I wrote the square root of x as x to the 1/2 and then did the process that way. So 1/2 multiplies down front, and then that gets smaller by 1. 1/2 minus 1, negative 1/2. So that's h prime. So there's h prime. Now, technically, that's the derivative. You always want to simplify, though. So put some things together. This is x to the 1/2 right here. So x times x to the 1/2. And by the way, that's 2 halves there. So that's where x to the 3/2 comes from here. Likewise, over here, multiply, add the exponents when you multiply numbers that have the same base. So 4/2 and minus 1/2, that's where the 3/2 comes from. And now, because I have the same variable, x to the 3/2, x to the 3/2, I can add up the coefficients. 2 plus 1/2, 2.5, 5/2. Now, just for giggles and kicks, I'm going to come back and do this one differently. The point of that was to kind of see that the product rule, how the product rule works when I have the derivative of a product. I could have, at the very beginning, taken these two things and multiplied them together. And if you had to do this problem, that's what you should have done. That wasn't the point at the beginning. The point was to see the process. But just given this problem later on this year, you should not treat this as a product. You should say, oh yeah, I can simplify this expression to this. And now do the derivative. 5/2 comes down front. Exponent gets smaller by 1. Same answer, right? So 5/2 x to the 3/2. That's the derivative. That's the product rule. And we're going to start doing that with much more complicated things. Sines and tangents and a variety of things. Here's another exciting one. Let's read it. So the derivative of a quotient. That's your problem from last night. It says you take the derivative of the first thing, which is the numerator, times what's in the denominator, minus the numerator times the derivative of what's in the denominator, all over the denominator squared. Here's how I say this. Not like that. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. That's how I say it. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. I've done this before, though. And if you did it in the other notation, it would look like this. derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. So let's try an example here. We can do this with the limit of the difference quotient. It would just be darn uncomfortable and take us a really long time. Conveniently, somebody's figured out some stuff for us. We just get to use their answers. Aren't they nice to share with us? So, got to take a derivative. The numerator, we call this the f of x if you want to. Call this the g of x. So the pattern is derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. So the 2x is the derivative of the numerator times the denominator minus the numerator. Derivative of the denominator is just 3. All over the denominator squared. I will always want you to simplify if you can. So FOIL, well, distribute, and simplify. That's it. So another example, and just watch this one. These are stuff like this in the book. Find the derivative. So because it's a polynomial, you're just going to take and do the derivative of each one of those things separately and write it down. So the derivative of this, the exponent multiplies down front, get the 6. The exponent gets smaller by 1. 2 times 7, that's where the 14 comes from, smaller by 1. Now you can do this one the same way. 1 times 2 is 2, and then becomes x to the 0 power. And x to the 0, of course, is 1. And then the derivative of a constant is 0. That's the derivative. 6x squared minus 14x plus 2. Similar kind of a thing, it's quotient. So we're going to take a derivative. Derivative of the numerator, 2, times the denominator, minus the numerator, derivative of the denominator, all over the denominator squared. Be able to say that saying and be able to write this out. So that you can take the derivative well, quickly. Derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. So, and then you simplify. That's it. Those are the rules we pick up in next section. So we already knew the polynomial thing. We picked up the product rule and the quotient rule out of here. And a lot of what we'll do is just practice doing a bunch of them. Later on, we'll put meanings to those. What is the derivative? Sometimes the derivative means something, right? Okay. Sometimes the derivative means something. If we're talking about position, then derivative means velocity. Derivative of velocity is acceleration. So there's a lot of physics applications for the derivative. There's business applications. What's called the marginal cost is the cost of producing the next item. And the marginal cost and the marginal revenue is a big deal if you're in a business environment. And that's the slope of the tangent line, which is the derivative. So all of those things kind of come together. The end.